specific look today at what we saw yesterday in this little preview of what's called vertex form. Why do you think it might be called vertex form? Why do you think it might be called vertex form? Think about what you did yesterday with the calculator. Why might it be called vertex form? Like, why isn't it called standard form? Granted, you know what standard form looks like for a quadratic, ax squared plus bx plus c. What is the significance of the word vertex in the name vertex form?
They're quadratics in relation to the vertex.
So?
0, 0.
Yeah, it's all quadratics and they're comparing it to the parent function. And what's changing really? They're comparing the vertex, really. The original vertex of the parent function is 0, 0. The minute you introduce h and k, these translations, these shifting values, these parameters that cause the graph to shift, you now have a new vertex. So that's why it's called vertex form, because h and k actually indicate the actual vertex. So let's take a look at this standard form, this vertex form for this example, about the axis of symmetry. So we did this with your calculator yesterday, whether you realize it or not. For either of these, if you start at 0, 1, 2, 3, we'll see that these are just squares of each of them. Okay, just an idea to see what the parent function looks like. And this was what you started graphing yesterday. Okay, it was that. Just the parent function for y equals x squared. And that's the beginning of this whole concept. Then we went on to talk about the idea of what happens afterward. Well, do we have, in this case, an axis of symmetry? What does an axis of symmetry mean? And if you haven't heard the term before, use context clues. Axis and symmetry, those two words, how do they relate?
It's like the middle of the graph.
Yeah, so what line would that be in this case?
The y-intercept thing.
The y-axis. The y-axis happens to be our axis of symmetry. What is the equation for the y-axis? What is the equation of the vertical line that lies on top of the y-axis? Yep, x equals 0. Because remember, x equals 1. Isn't x equals 1 out here? And x equals 2 is over here, etc., etc. That's what our vertical lines look like, x equals. So x equals 0 happens to be the axis of symmetry here. Let's keep that in the back of our mind. We also recognize that this graph is concave up. This graph is concave up. And what does that mean again? Somebody tell Alex what he missed for concave yesterday. What does the word concave, up or down mean? What is the term concave up or concave down? This is concave up. If that helps you to give the example, Morgan. Yeah, so the way the parabola opens is called concavity. So concave up is this. Concave, C-O-N-C-A-V-E, concave. Concave down is this. This graph is concave up. And we're going to see that that's because the A value, obviously. Okay, again, a lot of the stuff you saw in that activity, but I'm just trying to go through it so we reiterate these topics. And then obviously the vertex is at the origin. Right? The vertex is 0, 0. We know that a vertex of a parabola is either a max, or what's the other term? Opposite of max? Min. Okay, it's either a max or a min. It's one or the other always. Okay, a vertex always represents an extreme. You're going to talk about this so much in calculus, these ideas of extrema they're called. The peaks and the troughs, the crests and the troughs, the valleys and the mountains, whatever you want to call it. But the tops and the bottoms of different curves when they start to turn around. All right, so to see this, we started to change letters, right? We said, you know what, let's see what happens. And instead of, going through every single step, I'm going to show you a lot of this because you saw it yesterday. When it was y equals negative x squared, what did that graph look like? Who could recall from yesterday what the graph of y equals negative x squared looked like? How did that differ from x squared? What's the only difference? Yes, it's literally the same thing, but concave down. But concave down. Now, we also talked about the width of a graph. Let's take a look at another example of this, where we have a graph we want to see what's going to happen with the width. negative portion. We're going to see the comparison between these two. By the way, graphing tool, good graphing tool, if you ever want to come up with your own graphs, I use what's called Wolfram Alpha. Wolfram, Wolfram, like Wolf, Ram, one word, Alpha. It's a good website for checking your homework and stuff. You can literally put any problem in there and it will do it for you. I'm not saying to you, I'm telling you guys this because you're honor students. I would not tell a class that wasn't. Because so many students just wouldn't do their work and they would end up just doing it on the computer. But you can check every single homework example, every single practice problem on there. You could literally type anything in there and it'll be able to do it. The only time it runs into problems is if you use like word problems. It can have trouble with those. But it's like a computer that actually, or it's a program that actually solves them for you. So that's where I got this graph, by the way. I just typed in y equals x squared and y equals negative x squared, and I put them on the same graph so you can see the comparison. And you could also use GeoGebra, that program I just had, to graph things. It's very, very powerful. It helps you with a lot of different transformations and things. So the question was, well, what if a, instead of being just negative, is also a different kind of number? So we saw when a was negative, it's concave down. When a is positive, it's concave up. Another statement, and this is what it was. Look at the graph on the far left. And on the far left here. We can see that when the coefficient a is a decimal, like 0.5, the graph got wider. The graph got wider. But when the coefficient a was a number that was greater than 1, such as on the right, see this 2 here? This 2x squared is that little like magenta line. Anybody colorblind? I think I've asked this before, but remind me again. No? Okay. So this little like purple magenta-ish line, the 2x squared on the right here, that line is clearly indicating that, you know what? If a is greater than 1, the graph's going to get narrower. Well, you can combine these two and you could say this is one that we had a minute ago. Well, what if a is negative n, it's greater than 1, like negative 2, meaning greater than 1 in value. It gets steeper or narrower again like this, but it becomes on the negative side of the axis. And then you saw this in your example that if a is 0, if a is 0, it's just the line y equals 0, which is just the x-axis goes across. So we'll see that the general idea is that as a gets smaller, the graph gets wider. If you want to underline that or highlight it, whatever you'd like, is right there. And then as a gets larger, the graph gets narrower. Okay, again, forget the negative part for a. The negative part only indicates if it opens up or down. When you're trying to see if it's narrower or wider than a traditional parent function graph for this, look at the actual value of the number, not the negative sign included. Okay, don't look at the negative sign to help you with the width of the graph. You could think of this as steepness, if you'd like. Think of it like a line. If I have a line with a slope of y equals x is a slope of 1. Y equals 2x, y equals, I'm doing it from your perspective. Y equals 3x, y equals 4x, until the graph becomes a vertical line and the slope is infinity or undefined. So what we're seeing is that the slope is going up. Well, everyone teaches y equals mx plus b, but remember in the beginning I was like, well, it's the same thing as y equals ax plus b. You could write any linear function as, 3x minus 7, 4x plus 2, 3 halves x minus 12. It doesn't matter. All that matters is that first value indicated the steepness. It's the same thing here, really. That a value, the leading coefficient, indicates how much the graph changes as it moves. So if it's steeper or if it's wider. Like if it rises slower, you're going to have a decimal value. If it rises really fast, you're going to have a number greater than 1. Think of it like slope of a line if it helps you. Okay, you increase that value, it gets steeper. It shoots up much quicker. Okay, much quicker. So that's the effect of A. Let's take a look at the effect of K now. All right, look at the effect of K. And the general equation, if we recall, is still this. All right, that's the general equation right there. But because we haven't done H yet, I said, well, we could start by looking at this equation right here. Because we didn't really talk about H just yet, so make believe H doesn't exist yet. And what we're going to notice is this. The graph shifts upward when K is positive. And that's what we talked about yesterday at the end. And the graph shifts downward when K is negative. And we can see that here. 3 takes the place of K in the second line, this magenta line. 3 literally takes the place of K right there. So as a result, if a positive 3, again, a positive 3 takes the place of K, I know it's a positive 3 because y minus positive 3 is what I'm seeing here. So this 3 is K, which indicates that this is shifting upward 3. So go up 3, and there's your vertex right there. If I looked at this one here, how can I get y plus 4 if I were writing it as y minus? I would write it like this, y minus negative 4, and that equals the rest. Okay, and minus a negative is what gives me a positive. That's where this comes from. So as a result, k is negative 4. When k is negative 4, it means we take the parent function and we simply shift it down 4 units. Okay, down 4 units. Remember, please, that when you're graphing on a calculator, you can't plug in the calculator y minus 3 equals x squared. It's impossible. So you have to take the negative 3 and add it over here as a positive 3 and write it as y equals x squared plus 3. And then if you see a plus 3 over here, you could think of that as a vertical shift up 3. Whereas if it's on this side, you have to kind of do the opposite of what the sign is that you see there. Right? You're kind of seeing a negative 3, and it goes up 3. Here you're seeing a positive 4, yet it goes down 4. So some students try to remember, okay, just do the opposite of what you see there. Okay, do the opposite. But if you look at the standard form every time, or the vertex form every time here, you could clearly see that the number 3 replaces k. So go up 3 units. If it's in this form. Okay, if it's in that form. Applies, but now for h we have to recognize that it's no longer causing a vertical shift like k did, but a horizontal shift. But it's the exact same scenario. It's the exact same scenario. The second equation we have there is x plus 3 quantity squared. Well, the only way to get this is to have this. Right? Minus the negative is really where that comes from. Well, take a look. If I look up here, I see that h is right here after the minus sign. Right? X minus h quantity squared. Well, this h is right here, and here we have a negative 3 here. So h, in this case, would become negative 3, the opposite of this number, if you want to remember that. So if h is negative 3, this graph has to shift over 3 units to the left. 1 unit, 2 units, 3 units. There's the vertex. The last one is showing the exact same thing as we saw with k, but with a minus sign. Think of this as h is equal to 4 now. Okay, h is equal to 4, so we move over 1, 2, 3, 4 units. So this bottom one is represented by this green curve right here. The goal of this overall lesson is to put everything. So let's go ahead and do that with this example so you can see it visually here. Okay, this is just the intro theory. I want to get to the examples that we're going to do mathematically next. So if I look at this right here, I'm going to see that k is 1 and h is 2. K is 1 and h is 2. So if h is 2, I move 2 units right, and k is 1, I move 1 unit up. There's my new vertex right there. So as a result, I can label this as 2, 1. But remember, h was 2 and k was 1. So that tells me that the vertex is always going to be h, k. Whatever you have for h, in this case 2, whatever you have for k, in this case 1, will always become your vertex. So your vertex is 2, 1. Exactly what we showed there. Alright, so this is a big key point right here. And I think I wrote it. Yeah, I did write it in the paragraph. Okay, we can see that from the shifting, this also dictates the location of the vertex. Okay, it's always going to be h, k. Now, what you should also recognize this time, and this is not obvious though, is the axis of symmetry. Where is it for the dashed line graph? What is the axis of symmetry for the graph that is a dashed line? What is it, Jeff? X equals 2. Well, where is it? Here it is. I'm drawing it in blue so you can see it. Usually you draw an axis of symmetry with a dashed line. And it's x equals 2. Well, what is 2 in this problem? What parameter is 2? H. H is 2. The axis of symmetry is x equals 2. So in general, we can say that the axis of symmetry has been changed and it's now the function x equals h. It will always be. Axis of symmetry will always be x equals whatever h is. So the key point here is to recognize what a, h, and k are. Okay, a, h, and k. Questions on this one right here? Notice that I wrote again that if A had been negative, you're just taking the graph, and instead of opening up, open down. Okay, same graph. All right, so the theory's done. Let's get into some examples now. All right, so the first one is pretty simple, but just go ahead and think about what you would have. List A, H, and K. Write out what they are, what they mean if you have to. Graph your parent function. And once you get A, H, and K, graph the actual other function. That's just the parent function right there. Morgan, what's A?
Would be 2.
Not 2. Let me write out the general form. Maybe that'll help you. -1. Okay, A is -1. What's K, James? What's K?
2.
K is 2. Very good. And Alex, what's H in this one?
3.
Be careful.
-3.
-3. And that's the trickier part, you know. The general form of the vertex form is written as x minus h. So to get a +3, this really means x minus -3. That's really what that says. So it's a -3 that takes the place of that h right there. Okay? So those are our 3 parameters. If hk is -3, 2, I go left 3 units. And then I go up 2 units. Again, left 3 units. And then up 2 units. There's my vertex right there. Okay, I put those little bubbles to show me moving, but it's just 3 units, okay? 3 units left, and then 2 units up. So, there's my vertex. Am I done? Is that all I need? What other information can I utilize? Well? It opens down. Is it going to be wider or steeper than the parent function? Steeper? Yeah? Careful. If it was a number like 1.1 or 1.2 or 1.3, anything bigger than 1 is definitely steeper. It's the same. Very good. It was kind of a trick question. I'm glad you noticed that at the end. Okay? It's going to be the same width as the parent function. So this graph is not going to get suddenly much wider because it's not an A value that's a decimal or fraction. The graph is not going to get much steeper because A is no longer a value that's like 2, 3, 4, some greater than 1 value. All right? Is that clear with that? Okay, simple example of that. Now, the next problem, or the next thing we're going to talk about, we're going to go back to the idea of roots and solutions and intercepts and relate it to this idea of the vertex form. Okay, this is stuff that we've been talking about already in class, but I want to talk about intercepts and quadratics. And we've discussed this. Can somebody explain what's happening here? Can somebody explain what this image is showing or what's being stated on the left? And you've seen this before. You've seen this already in the section when we covered the discriminant, 7.3. 7.3, you saw this already. Any ideas what this graph is indicating here? I'm not asking this for like a random reason. You'll see where it leads in a moment. What is it showing? What is it demonstrating? Well?
If D is greater than
What is D, first of all?
the discriminant,
Good. If the discriminant is greater than 0,
then it has 2 x's,
x-intercepts.
x intercepts, and if it's 0, then it has 1. It'll be the vertex, and if it's less than 0, then it won't have any.
Yeah, and remember what we talked about with the discriminant? When the discriminant was negative, what kind of roots did you get? When the discriminant was negative, what kind of roots did you get? What kind? Imaginary. So you need to literally imagine that you have roots, because you don't. There's no real roots here, because remember, roots are x-intercepts. And if your roots are imaginary, you can't have x-intercepts. So this third case is either floating above the axis or below the axis, one or the other. The second case we looked at was what if the discriminant is 0? When the discriminant was 0, what kind of a root did we get from that? When the discriminant was 0. One real repeated root. Where is that? It's right here. It's right there. There's the repeated root. There's only one of them. It touches the axis. It's what we call tangent to the axis, and then it returns. Okay, tangent. Maybe underline this right here, okay? Tangent to the axis. Tangent means touching once. And then finally, with the discriminant was positive, we got two real roots, and usually they were binomial conjugates, or sometimes they were rational, but the idea was that there were two roots. Here's one of them, and here's the other one of them. Okay, we have two roots when the discriminant is positive. Let's take this idea and apply it to vertex form. Okay, to vertex. So for this one, I want you to identify the vertex, the axis of symmetry, and then find the intercepts. Okay, we could do the vertex and axis of symmetry easily. So you start doing that, I'll start writing it up. Then when we get to intercepts, I'll take your advice and see what you think we should do. Make sure you understand where these parameters are coming from. If you don't, look up at least and check your work to see if you're doing it right. Y plus 3 means that k has got to be negative 3. X minus 2 means h has to be positive 2. And the 2 in the front is indicative of the a value. So what's the vertex? What's the vertex? What's the vertex, James? 2, negative 3, very good. And what is the axis of symmetry, Chandler? X equals 2. Remembering that the vertex is really just HK. And the axis of symmetry is always X equals H. Now, how do I find the intercepts? That's the follow-up question. How do you find intercepts in general? Forget this problem. If I said to you, what do I do to find the y-intercept? Answer that.
It's the value of y when x is 0, so you set x to 0.
Set x to 0. And how do you find the x-intercept then?
Set y to 0.
Set y to 0. So go ahead and do that. Find the y-intercept first. It's a lot easier. So you set x to 0. And there's the 0 right there. Make sure you set it equal to 0. And then just solve for y. Just solve for y. This is going to be negative 2 squared, which is 4. 4 times 2 is 8. 8 minus 3 is going to give us 5. So my y-intercept is 0, 5. And to find the x-intercept, we set y equal to 0. Well, this is really interesting. Watch this. Ready? 0 plus 3 equal to 2 times x minus 2 squared. So again, I take the original function and just plug a 0 in where I see a y, where I had the 0 in earlier for the x because I found the y-intercept with the x back. If you try to solve this for x, how might you recommend going about solving? There are two ways. One is more difficult than the other. One is more difficult than the other. Do you recognize this at all? You see a similarity of the form of the equation compared to what we've seen before?
It would be like completing the square.
Yes, very good, Jeff. This is completing the square. When you complete the square, when you're done, you always got something like this, didn't you? You had something squared, and you had some number on the other side. So get rid of the 2 first by what? Divide by 2 first. Okay, divide by 2. Give me another minute. Take the square root of both sides. And then add 2 over. Now, before we conclude for today, answer this question first before you can leave. What kind of roots do we have here? When you see 2 plus or minus root 3 over 2, what kind of roots are these as an example? What kind of roots are they? Jeff? Be careful about complex conjugates. Complex conjugates mean that they're imaginary, right? Complex meant the imaginary part. Binomial conjugates. Okay, these roots, although they look messy, they're numbers. If you look at them on the graph, you would literally do 2 plus radical 3 halves. 2 minus radical 3 halves. That's where your x-intercepts will be. Okay? What I want you to do tonight is the following. Let me see if I want to do anything besides that. I would like you to start the homework. The homework I gave you, so this is why I didn't put up the notes on Moodle, I realize now. I wanted to alter the homework a little bit. Last year I just gave you 3 from 30 multiples of 3. But I wanted to pick specific questions. So tonight, here's what I want you to do. Do numbers 3, 9, 15, and 27. I'm just going to pick random ones out of there. Okay, in section 7.5. Do those at least. If you have not completed this or finished this, or the idea, make sure to finish what you're doing. Aside from that, tomorrow we'll clean up with these, or not tomorrow, the next day. With these, actually, no, the next day we're in the gym. Tomorrow, no class. Friday, we're in the gym. Third period 3, come there. The app I want you to download, I will send you a link to in your email. Okay? Not everybody really needs it. You might work in pairs. It costs like $4, so if you want to split with somebody, it's fine. Sure. You're welcome, Chandler. All right, so in example 3, we'll have this in front of us. I'm going to read as we talk. So we have graph y plus 2 equals negative quantity x plus 3 squared. So graph it. And then part 2, identify the vertex, the axis of symmetry, and all intercepts. So a similar problem, but now we want to actually see what the graph of this looks like. So first of all, we see that we have y plus 2 equals negative quantity x plus 3 squared. So what's h, k, and a? Let's identify those first. H, k, and a. What do we have for those? Give me one of them. K is negative 2. Agree, disagree? K, negative 2. Yes, right? Because again, look at the original function here. The general vertex form is y minus k. So it has to be y minus negative 2 for this to fit in to be y plus 2. And remember that for k, you could really just take the opposite of what you see right here. Okay, whatever the sign is, if you want to just take the opposite of it, that's fine. What about h? Or a, yeah. A is negative 1. Very good. A is negative 1. That works. And then h. H. Somebody else? H. Jenna? Negative 3. Okay, again, because a comes as the coefficient of this whole thing, whereas h comes as this addend, this thing that's added on. And we remember that we could think of the opposite of that sign if we want to, because the vertex form is x minus h quantity squared. So we've identified those 3 things, which are very useful. What does A tell me about the graph? Remind me what A tells me about the graph. What does A indicate?
Like what's the width and whether it opens upward or downward.
Very good. The width of the graph and the direction it opens. Since it's a 1 or a negative 1, the width doesn't change. Remember, only if it's a fraction or a decimal or a number greater than 1 in absolute value does the width change. But in this case, it's negative 1, so the width is the same, but because it's negative, it opens down. Remember that if you want to write it, you could write it's concave down. Okay, concave down. H and K. What do H and K tell me? What do H and K tell me? Yeah, the vertex. Okay, the vertex is going to be negative 3, comma, negative 2. H, comma, K, always. Remember, it's the horizontal shift for H and the vertical shift for K. The axis of symmetry. How do I get the axis of symmetry? What does the axis of symmetry always go through? Let's answer that question. What does the axis of symmetry always go through? It always goes through H, or the vertex, right? We'll say. It always goes through the vertex, and it's always H. So it's x equals -3. The axis of symmetry is x equals -3. It always goes through the vertex. Next, I need my intercepts. The y-intercept is much easier to find. Find that first. To find the y-intercept, set x equal to 0. What do I get for the y-intercept when I do that? What do I get for the y-intercept? Well, -11. Very good. Okay, be careful because it's the opposite of 3 squared. It's not -3 squared. Again, on the right-hand side here, this is the opposite of 3 squared. 3 squared is 9, which makes that -9. And then when you subtract 2, you get -11. So 0, -11 for the y-intercept. For the x-intercept, set y to 0. Now, what do I do to start? Be careful here. What do I do to start? And yesterday Jeff told us that this is like completing the square. We have 2 equals that negative or opposite of the quantity x plus 3 squared. Okay, this is what we have right here. What do I do? What do I do next? Divide by -1 to get rid of the a value there, which makes it -2 equals quantity x plus 3 squared. Please don't FOIL this out. Please, with vertex form, do not FOIL it out. Because then you got to go do the quadratic formula, which is so much more work. It's already completing the square. Now, what's going to happen next? What's going to happen? And what happens when I square root it? Yeah, but what do I notice when I square root this? What kind of an answer am I going to end up with? Louder. Imaginary. Why, Sarah? Why do I get an imaginary answer for my x-intercept? Yeah. You're going to have to take plus or minus radical -2, and that's going to equal x plus 3. So you'll get, -3 plus or minus I root 2. That's what x is going to become. Well, as soon as you take a square root and you're looking for the x-intercepts and it's imaginary, you could stop. So as soon as you get to this stage right here, where I circled it, you could kind of stop there and say, well, the roots are going to be imaginary. And imaginary roots don't show up on a graph. So there's going to be no x-intercepts. This graph will have no x-intercepts. How else do I know that? Ready? Here's what I could do. Go ahead and draw yourself a graph, please. The vertex was what again? What was the vertex? Go back up, James. -3, -2. So I go over 3, and I go down 2. And I put a point there. There's my vertex, right? We all see that? Which way does this graph open? Which way? Why? Why does it open down? A is negative. So look, draw a graph opening down. Are you going to have any x-intercepts when the graph opens down? No, you're clearly not. If the graph starts below the x-axis and opens down, you're not going to have any x-intercepts. That's the reason that your x-intercepts turn out to be imaginary. And what was the y-intercept again? What was the y-intercept? What was it? -11. Okay, -11. So all the way down here somewhere. Okay, so if you want to continue to extend your graph, it's down there at -11. Well, that means that you're going to have another point symmetric on the other side at -11 also. Okay, so you've got your vertex at the top, and you've got your y-intercept. You've got another point on the other side of the axis of symmetry, which is right here. Here's the axis of symmetry. Okay, it's not the y-axis, it's the axis of symmetry right there. This is the y-axis right here. Okay, this is the x-axis over here. That's what your graph generally is going to look like. So use symmetry in your favor. If you need another point on the other side, literally mirror it over. Okay, it's going to be 3 units over. 1, 2, 3 units over. How do I know it's 3 units over? Because the vertex starts at -3. So that's 3 units to get to here. So it's also 3 units to get over here as well. Okay, this will be 3 units away. These are 3 units here, and this is really 3 units distance here. I know it may not look symmetric because I'm drawing upside down right now. Okay, it's difficult. But these are 3 units away on both sides. All right? So imaginary roots indicates to you right away, what should you do? You should stop and not even go to find the x-intercepts because there's not going to be any x-intercepts. All right, when you get imaginary x-intercept values or roots. Let's find an equation of a parabola having a given vertex and containing that point. Well, you have the vertex, which is hk. So plug in right away for hk. When you plug in for hk, what does the general equation become? Only hk, please. Leave a alone for now. When I plug in for hk, what does it become? James.
Y plus 4 equals a x minus 2.
Very good, James. It's y plus 4 because it was really y minus -4 equals a times the quantity x minus 2 squared. Again, I know that because I take h and k from the actual vertex. H is 2, k is -4, and plug them into those respective points in the vertex form. How do I find a? Let's see who could really figure this out. Come on, who knows their stuff? How do I find a? Daniela?
Do you plug in 5 and 14 for x and y?
Yeah, you're given the point 5, 14. You've already used the vertex, so cross it off. You don't need the vertex, you've used it. But plug in 5, 14 for x and y, and then solve for a. So plug in a 5 for x, and a 14 for y. And the rest of it remains the same, and you could simply solve for a. Okay, take a look here if you don't understand. If you want to look up, you can. Plug in 5, 14, you'll see it in red. Okay, plug in 5, 14 in that location and solve for a. Which will give me, let's see, 18 on the left-hand side equals a times 3 squared. So what does a become? 2. Okay, it's going to be 18 equals 9a. A equals 2. So my answer, y plus 4 equals 2 times the quantity x minus 2 squared. Okay, here's my answer over here. Again, y plus 4 coming from this line right here. Look, this is the line it comes from. Repeat this over here, but instead of an a, you're putting a 2 in place right there. Is that clear? Okay, so vertex form. That's the end of vertex form. So tonight, make sure to practice the rest of the homework. Right now, I think it says 3 through 30 multiples of 3. I'll email you with an assignment specifically that I want you to do. Okay, so don't start 3 through 30. Last night, you practiced the ones I gave you, right? I'm not going to check those. I assume that you're doing your work. All of you usually do your work. So you did the ones I asked you to practice. But I'll email you an assignment for this, okay? Because I'm going to change. It's not going to be 3 through 30 multiples of 3.